All right, so what I want to do today is actually kind of solve homework 4 and derive the residual for the linear momentum balance problem. That's my goal for today in both the reference and the current configurations. And I will also walk you through the solution of homework 4, which I've already finished, and I'm posting also to Brightspace. So recall that the main integrals that we need for the linear momentum balance are, there's some other terms, but the main integrals that we'll have to calculate are the integral of the second pure Kirchhoff stress contracted with the variation of the Green Lagrange strain, or if you are in the current configuration, you can compute the integral of the Cauchy stress double contracted with the variation of the symmetric velocity gradient. And we are going to compute this over an element. And so just to give you a refresher of the discretization. So we have the weak form, and then we want the discrete weak form. And for the discrete weak form, we need the discretization first. So for the discretization, what we have is, for example, for the linear quadrilateral, we have some nodes, and we have the coordinates of the nodes, both in the reference and the deformed configuration. So x1e, x2e, x3, x4e are the coordinates of the nodes in the reference, the capital X, and the lowercase x1e, x2e, x3, and x4e are the deformed coordinates of the nodes of the element. And these are vectors, so these have x and y components. And we introduce this parent domain. So this is reference, this is deform, and this is the parent domain. Xi and eta, or for short xi. And then in the xi space, we always have the same domain -1 to 1, because we can do integrals in the -1 to 1 relatively easily. The connection between this parent domain and the reference coordinates is the isoparametric map using the reference coordinates, and that's here. So that will be the sum of the shape functions, which are defined in the parent domain. So the shape functions are naturally defined in the parent domain. You just have to look them up. And so the sum of the shape functions times the nodal values, the reference nodal values, give us the points in this here. So for every point that you choose here, you will get a point in the X space in the reference configuration. So that will be the isoparametric map for the reference. You can pose a very similar interpolation for the deform. So you just need to use the same shape functions, but now the deform X coordinates. And then again, just sum of shape functions times the nodal values means that for any point that you pick in the parent domain, xi and eta, you will get the corresponding point in the deformed configuration. And we've done at least one Python notebook showing that, and in one of the office hours, I did a Python notebook where I showed this for a quadratic quadrilateral. So that is the isoparametric map. It connects the parent domain coordinates xi to the deform, either the reference or deform coordinates x, capital X or lowercase x. Now, in addition to having the isoparametric map, we have the Jacobians. And here, because we are thinking about two isoparametric maps, we have two Jacobians. We have the Jacobian of the isoparametric map that takes us from the parent to the reference. And so that will be, here I use the capital J, which is the same as in the book. And that's the derivative of x coordinates with respect to xi coordinates, and is the sum of the nodal x's dyadic product with the gradient of the shape functions with respect to xi. So this gradient is with respect to the parent domain coordinates. And this one is the easier, the one that you can calculate in a straightforward way, because you have the shape functions in terms of xi. This just means take the gradient with respect to the xi. So that one you can do analytically, and you can code it. The Jacobian for the other isoparametric map is similarly just the sum of, but now the deform x's, again, dyadic product with the gradient of the shape functions with respect to the xi coordinates. Having the Jacobian, you can now compute gradients with respect to either capital X or capital or lowercase x by chain rule. So what that looks down at the end, I've done the derivation, but in the end, basically what you get is the gradient with respect to x, capital X of the shape functions is just the Jacobian, the corresponding Jacobian minus transpose times the gradient of the shape functions with respect to xi. Similarly, if you want a gradient of the shape functions with respect to lowercase x, then you have the Jacobian of the other isoperimetric map times the gradient of the shape functions with respect to xi. And finally, the main object that you actually want to compute is the deformation gradient, which is the derivative of the little x with respect to the big X. A couple of ways you can calculate it. You can do this. This is basically just chain rule. So the Jacobian of the one of the isoperimetric maps times the inverse of the other one. Or the other one that I think is the one that I gave in a previous lecture is the sum of the deformed coordinates, dyadic product, gradient of shape functions with respect to x, which you need to calculate from this formula right there. So that's the first thing that you needed to compute in your homework was basically this. So given some new coordinates x a and some original coordinates capital X, compute the deformation gradient. And again, I will show you the code for the homework in a little bit. So this is the main overview of the discretization and how to compute the deformation gradient based only on the reference and deformed nodal positions. And once you have the deformation gradient, you can compute things like the stress, for example. So once you have deformation gradient, you can always compute all the kinematics and the stress. Compute any kinematics and stress. So you can compute, for example, B equals FF transpose, and you can compute sigma, like I said in the homework, 1 over J, now I forgot, what was the C1 times identity B times B hat, if I remember correctly. 1 over J C1 plus B hat plus P times identity, where P was something like D1 J minus 1. I think I'm missing a 2 somewhere, or 2 2's. In this have 2. Anyways, you can compute the stress. Once you have the deformation gradient, really just apply the formulas. You've done this before, how to calculate stresses. So that basically covers the problem 2, at least parts of problem 2 before the variation. So problem 2 of the homework up to part D, at least the derivation. So this is what I wanted you to do. And then in a separate video, I will have the Python code where I actually compute it. So I'm gonna stop right here, and I'm gonna do another video for what is basically parts E, F, and G of the problem 2 of the homework.